All right, welcome everyone to this last day of HoTT-UF workshop for 2020. So before we start, I'm just gonna remind you of the rules that you hopefully already know. So if you have any questions, save them for the Q&A unless they're super important. And please, oh yeah, I'll monitor the chat and the raise the hands in the participant list. So if you have a question, raise your hand and I'll unmute you. But if I don't notice, please just unmute yourself and ask your question. All right. Okay, I think those are the most important rules. And so I have the pleasure to introduce Andrei Rodin, who will talk about computer-assisted proofs and mathematical understanding, the case of Univalent Foundations.
Yeah. Thank you, Anders. Good time of the day. So I'm a philosopher, and I'm mostly learning maths in such events like this. But I'm very grateful to organizing for giving me opportunity to give a philosophical talk. And as I already mentioned to Benedict, a great advantage of talking to mathematical audience in my case is that I should not explain mathematics and can go straightforwardly to philosophy. So, so I will talk about computer-assisted proofs and mathematical understanding, and I will consider Univalent Foundations in that context, and I will argue that there is indeed something very special about Univalent Foundations, and in particular that it's, say, solves certain problems which have been raised in different contexts with different cases of computer-assisted proofs, and indeed Univalent Foundations solve that. So this is the plan. I'll talk a little bit just generally about automated computer-assisted, meaning proof verification, then consider example of four-color theorem, and actually I will not consider the theorem itself, but these philosophical discussions around it, and that will lead us to general question, which I of course touch upon very briefly. What is a proof? And a little bit more specifically, I will talk about the role of intuition, not even in all mathematical proofs, but also in formalized, informal proofs. And then I will discuss homotopic intuition in Univalent Foundation and come to my conclusion. So here is a timeline for automatic proof. I will not comment. There are actually two overview. One is a little bit outdated already, and the other by Jeremy Avigat from Cornell Mellon, relatively new. For some reason, he doesn't talk about univalent mathematics at all in this overview, but that's, I think, important just to have to understand that this effort just made by this community, then the context is much larger context. And I will make just two, say, observation about all this. So I mentioned, first I mentioned prehistory. I will not talk about Leibniz in this talk, but talk about a little bit about David Hilbert and his famous program. And the interesting observation is that this whole development, which started in the 60s, actually did not follow this Hilbert's ideas of how it should who had this vision of how it should work, and involved also quite a lot of technical work, as we all know. And thing is that all these systems use types in some form or another. Some proof like Mizar, they were not actually motivated by type theories, rather by set theories. But anyway, they use them. And before yesterday, Carlo called this type theory in this context kind of sorcery. And I think a reason we may ask probably Carlo if he's here, but my guess why that word came to his mind like sorcery, exactly because we don't have kind of theoretical, philosophical justification or foundation. Why should type be there? So it looks like a trick, a technical trick, a sorcery, but I think we should actually change it. And second obvious remark, of course, that all those, say, formal systems which serve as basis for this already implementation, they are rather in Gensen style, rule-based style, rather than Hilbert style, axiom-based style, which is kind of natural when we are talking about the implementation. But again, I think that means that we should really reconsider our usual received ideas about axiomatic method. I would also know it really, this Gensen style provides a new dimension of what actually some authors like Nick Detlemsen called axiomatic freedom, meaning freedom to play with the axioms. And here we may and do play actually not only with axioms, but also with rules. That's something that Hilbert really didn't have in mind, because for him, rules were fixed and expressed rule of logic with a big L, something like that. And the key idea of this big project of revision axiomatic method, I have some papers on that. More recently, I have a habilitation thesis, which I completed thanks to this pandemic, which is found on my website. So key idea actually that we should not reduce mathematical theories, formal or not, to systems of propositions, and we should take, say, structures more seriously. But I don't want to commit myself saying that. I don't commit myself to this mathematical structuralism, so-called, because I think we also need to rethink what is a structure. And actually, that's not completely new, because actually in my earlier life, I worked mostly on Euclid and continue it in a way. I'll come in the end to that point. And then in Euclid, you also have theorems and problems. You have proofs and construction. So there is that kind of duality. So what we are talking about, it's not just something only new, but we have now in this new context, of course. Okay, so that's a more specific thing I'm going to talk about, is a part of this bigger project. So now talking about this four-color theorem, it was in 1977 by Eichel, Heiken, and Koch, and that was, usually it's quoted as the first important computer-assisted proof. I don't know how much it's historically correct, but at least was the first one important. Then more recently, it was reproduced, basically the same proof or similar proof with Koch. So the thing is that there is, of course, a normal informal part, but which comes down to about 1,500 special cases, which are rather hard and are not checkable by hand. So here where computer comes, right? And then it's provided a lot of discussion whether or not such a proof really qualifies as a proof. And I found this funny evidence by Appel, who presented it publicly somewhere in 79. And he says that public, earlier than 40, they couldn't believe that that handwritten proof in 700 page can be correct. And people earlier than 40, they couldn't believe, older than 40, they couldn't believe that computer proof would be correct. And that's funny, because that was already long ago, like 40 years ago, right? But still, this sociological observation, I think it remains almost stable. Yeah, so this philosophical discussion was started by Thomas Timoshko, who wrote that paper where he argued that accepting this computer-assisted proofs, mathematics becomes alike to experimental science, right? So we use kind of experimental equipment, computer in that case, and get evidence from that. So mathematics becomes somehow different from what it used to be earlier, and closer to experimental sciences. Well, there were a lot of interesting reactions to that. I will not talk about all of them, but there was one by Peter Taylor, who argued that actually Timoshko misconceives the concept of mathematical proof and verification of this proof, right? So his argument was that this formal proof, it may exist or not exist there, right? He does not judge whether it's correct or not, the given proof. But anyway, the existence of that proof, right, has nothing to do with our knowledge, with our epistemic access to the proof, right? So it may be not a proof, but how we know about that proof with computer or somehow else, that's simply irrelevant of a question. And that's interesting because that's conception of proof. Actually, that comes back to Hilbert and Bernays. Just proof is a syntactic inference with the only semantic part which is logical semantic, right? Semantic of rules. Actually, there are only two rules officially in that system: modus ponens and substitution. And so rules somehow, according to that semantic, guarantee that the derivation is truth preserving, and that's all. And there is no epistemic content actually in this concept of proof. And Doug Pravitz answered to the Stellar's argument more recently, and then he says that yes, the distinction between proof and verification is actually correct. We should distinguish this thing, but that notion of proof, which has no epistemic content, just does not make sense from Pravitz. So what we should consider as a proof is both this ideal, say, syntactic object and all means of epistemic access to that object. And that is actually, okay, I'll skip it, is based on Doug Pravitz's general view about proofs. And okay, I will not read it probably to save time, but basically he says that to preserve truth is necessary for being a proof, but not sufficient. And what we also need, that fact of truth preservance should be seen somehow in some sense, right? So that's already epistemic notion, and that gave rise to proof theoretic semantics as an alternative or probably some supplement to standard model theoretic semantics. And that's again a rather hot issue recently discussed, in particular last year in Tübingen. Yes, and here I only mentioned that it opens room for different ideas. Here it is a view of Yesenin Volpin in 70, who actually tried to use a kind of ethical concept to say that by proof of a judgment, I mean a honest procedure making judgment. Integrable and Permat and Löw on that conference last year in Tübingen also tried to bring in some ethical issue, talking about inferences, logical inferences. Okay, now I come to this more specific remarks about intuition. So it's a general picture that when we come to modern form of axiomatics, intuition is expelled somehow. The story about table, chairs, and beer mugs, I think everybody in this room knows. But interesting thing that when Hilbert looked closer, so to speak, in this earlier version, he did not use any symbolic logic, right? That was just general ideas about logic. But and that was second step of his project, if you like, when in his work with Ackermann, he came to mathematical logic in the sense of symbolic logic. Actually, he changed his view because he noticed, and quite correctly, that the whole enterprise of symbolic logic is based in certain sense of our ability to distinguish symbols, and it wouldn't work without that, right? So it's not correct saying in that formal presentation we don't use any intuition or it's not essential. It is essential, but that's a specific sort of intuition which I call finitary symbolic intuition. And then question is whether or not is this finitary symbolic intuition is sufficient to provide, say, evidence, to provide the epistemic force in our proofs, this evidential force. And basically my argument is that it's very good for looking into small fragments of reasoning, right? It allows one to distinguish details, logical details, which are not distinguished otherwise. But this is what I would call microscopic structure of proof, right? And the argument is that I use kind of biochemical analogy, that microscopic structure is important and maybe even basic in a sense that it determines all other structure, may be or not be. It's not really essential, but essential thing that this higher level structure, they actually matter as for proteins, say, physiologically, and the same in proofs epistemically. And more recently, I found a very interesting paper by Bradley Basler in 2006, who actually argues that we should, who also analyzes this four-color theorem, and distinguishes between local and global surveyability. And so he says, in the case of four-color theorem, there is kind of global argument, right? This informal part, which explains why this computation, if successful, will bring us the proof. And the local part, that concerns the code, basically, because at least at that time, code was all handwritten, right? So you can read it, a code, but you can see, you cannot see the whole thing. You cannot see why these little pieces of code just bring you what you want, right? And so I would a little bit make more precise my analysis in Basler line and saying that what we really lack in cases of computer-assisted proof like four-color theorem is that we have this, we do have this global picture somehow, right? We do have this microscopic evidence, right? But we miss kind of crucial mesoscopic level, which would allow us somehow understand the argument, to follow it, without going into minute details, but also something more than just very, very general picture that we do have in, say, four-color theory, right? And here exactly, I think that homotopical intuition changes very significantly the picture, because here exactly we have kind of geometrical intuition that which work on a level which is intermediate between, say, syntactic level, how we write a code, or say type theoretic syntax, and very general level, right? It introduces this, it supports intuitively this intermediate level in the form of, say, special homotopic-like construction. And then you can use, that's actually several people use it. It's very famous among philosophers, for example, by Frege, why morning star is the same as evening star, and in homotopic type theory just gives answer, you need a continuous path. If you really do have continuous paths, it's the same. It's a proof of identity in that case, okay? And yeah, that's a subtle point. Probably I have little time, but I would say that this homotopical interpretation, I think we should not think of as a modeling, right? Something like giving models to Hilbert-style formal theorem, like geometrical theorem. Rather, we should take it on equal footing with logical semantics, right? So it's a kind of fixed semantics. It's not about modeling. It's about giving default semantic for raw syntax, right? And that's supports this whole view that logic special case of geometry of Lovier, who made in context of topos theory. And I use this example of this theorem about fundamental group of topological circle after paper of Lecat and Schumann. And then in case you have a code in Coq and it's all intuitively supported that code. I also had a personal experience and now memory with Volodya Voevodsky, who tried to explain me something mathematics, just writing again a code and making some picture along, rather than writing kind of usual informal mathematical syntax, right? And so my conclusion is that roughly speaking, we may have two kinds of automated proofs. Oh, I'm sorry. Something, can you hear me? Something went wrong.
Yeah, I can hear you. Yeah, the screen sharing stopped, I think. But it was exactly when we were hitting the punchline.
Yeah. No, okay, I made
unfortunate.
No, so okay, I'll try not to stop to say it in words. So roughly, in one case, we use computer as a black box, right, which does some magic for us, and that's not good. And in that case, we have computer as a, say, assistant, which is no longer black box, but which shows what happens really inside. Okay, maybe I'll try to show again. to share screen again? No?
Yeah, very good. It's back.
I hope that it's not my PDF who's cramped.
Ah.
It shouldn't be.
No, it seems like it's working.
Yeah, so yes. So in case of UF, we do have a mathematical theory which is fully formal, right? Because it's in rigorous syntax. It is computer checkable and it's supported by spatial intuition, and that's a crucial intermediate level. And what is open problems, it's kind of project for future, I think would be really interesting to see where this, because my example, of course, is very special. It's from homotopy theory itself, right? So it's not surprising that this homotopical intuition really works well there. But question is whether that's the same intuition may also be relevant when we formalize, say, with Koch or cubical AGDA or whatever, some other areas of mathematics, right? Have we kind of reasonably transport this intuition to other areas of mathematics? And that's, of course, not obvious at all. And concrete proposal, my concrete proposal is about Euclid, kind of, again, rewrite Euclid in Univalent Foundation style, just as Hilbert wrote it, right, in his style. And I'm thankful to Mark Bickford, who a couple of years ago pointed me to his paper with co-authors, where we try to reconstruct Euclid's actually much closer to historical Euclid than usual reconstruction. And I think it could be also interesting, I never came across anything similar, but say develop software which would support, which would help, say, visualize in some form this, say, UF-based constructions or inferences. So that's just all this, gentlemen. Thank you.
Okay, thank you very much, Andrei. So let's have a silent applause for Andrei now. All right, thank you. Yeah, I'll open the floor for a few questions now. So please raise your hand or just unmute yourself and ask. Irina, yes, I think you're unmuted now. No. Did you want to ask a question?
Am I unmuted? Can you hear me?
Yes.
Yes, I can. Yeah.
Hi.
Hi.
Thank you so much for your talk. Hi, everybody. So, Andrei, how can we demonstrate these three levels, micro, meso, and macro, on the case of Euclidean geometry? It's a very simple question.
Yeah, no, it's a very good question. No, at least even on syntactic level, actually in Euclid, we have kind of proto-syntax, right? If we say triangle is ABC, it's not completely arbitrary name, right? It's constructed from points, from, how to say, apexes of triangle. By the way, Leibniz tried to use this idea to develop what he dreamed as geometrical characteristics. Right, so we have this kind of alphabetic syntax at least, right? And we have diagrammatic syntax, and we have just natural language. A lot too much, we would say, natural language. So that's rather clearly these three levels.
Okay, maybe one more quick question, if there is one. Okay, let me say something. So, so one nice thing with this Martin Löw style type theories are these meaning explanations, which you didn't mention. So, what are your thoughts about this? I mean, it's giving kind of a more philosophical justification to type theory.
What I think I actually try to write about that, it's very interesting indeed. pair system is very seriously, very consistently kind of philosophically grounded. And this kind of grounding, part of it survives in this homotopical context, but not all of it, not all of it. And no, simple thing is that actually pair believe that you can kind of interchangeably interpret given type either as proposition or a set or whatever. And so this homotopical hierarchy, of course, just makes things much more organized. But that's I think that's also changes upon his notion of judgment, for example. So there is a lot of things to think of.
Yeah, I think so too. Yeah, very good. Thank you. Okay, so let's thank Andrei again for this nice talk with a silent applause.
Thank you.
All right, so I guess we can start setting things up for Tom.